Okay, so the binomial theorem. This is out of section 4.2. And what we're going to do today is talk about how we can use the Pascal triangle, which we started to investigate today. It was something that looked like this. I'll add one more row. How that has something to do with our polynomials. So let me just put up an example here. We also talked about today how we have can multiply polynomials. So I'm going to put up here a binomial, okay, because there's two pieces, and so there's a this is one binomial, and I'm going to multiply it by another binomial, okay. If we distribute this out, we get x squared, xy times plus xy, and distribute that and get y squared. If we clean it up, we get x squared plus 2xy plus y squared. So that's the expanded form of these two binomials that are multiplied by each other. In other words, it's x plus y squared is equal to this. Okay? So let's just say, for example, we wanted to find another expansion. Let's say we wanted to find x plus y to the third power instead of the square. Okay? Well, what that is x plus y times x plus y times x plus y. Yeah? We already found x plus y squared. It was x squared plus 2y plus y squared. 2xy plus y squared. So then all we need to do is distribute it out this way. All right? So I'm going to go ahead and distribute this out. Okay? We have x squared, and it's going to distribute to the x, that's x to the third. X squared times y is x squared y. We've exhausted this term, and we're going to go ahead and distribute out the next term, which is this one. All right, and so I'm going to distribute 2xy times x. That gives me 2x squared y. Then distribute this one out to the y, and I get 2xy squared. That's squared. All right, so we've exhausted that second term in this trinomial. Now we have to go to the third term, which is the y squared. And if we distribute this to the x, we get plus xy squared. And then the y squared times y is y to the third. So let's go ahead and combine some like terms here. I only have one term that has an x to the third, so I'm going to write that in. I have an x squared y here, and I also have a 2x squared y here, so that makes a 3x squared y. And then I have a xy squared term here, and also an xy squared. So 2xy squared plus 1xy squared gives me 3xy squared. And therefore, y squared is the only term, y to the third is the only term that I have left over, and so I'm going to tack it on the end, and then our expanded, if we take x plus y to the third, we get this term right here. So now we can continue to do this with x plus y to the fourth, x plus y to the fifth, but I'm going to hopefully convince you or show you something, and you can go ahead and expand if you don't believe me, but we notice that the coefficient here is 1, okay? The coefficient here is 2, and the coefficient here is 1. Now notice the coefficients here. The coefficient, we don't really see it. We don't need to write it as 1x to the third. We have a 3, we have a 3, and the coefficient in front of the y to the third is also a 1. We don't write it, but we know it's there. So 1, 2, 1, 1, 3, 3, 1. And then I bet if you expand it more, you might be able to see a further pattern come up. So these numbers are starting to look like something we've seen before. 1, 2, 1, 1, 3, 3, 1. If we were able to expand x plus y to the fourth power, it's actually going to have the coefficients of 1, 4, 6, 4, 1. And so this is the binomial theorem, as we notice that this interesting numerical phenomenon occurs, and that helps us create and expand binomials by just using this pattern, all right? And so because this is, and I'll tell you, usually when we talk about the rows, we call this row 0, row 1, row 2, and row 3. So one of the patterns that occurs is that the row number, if matches the degree, so in this case it's x plus y squared, the coefficients are going to be 1, 2, 1. It's going to coincide with the row number. This case we had x plus y to the third power, which is a third degree polynomial, and the coefficients of the result is 1, 3, 3, 1. So even without doing a large expansion of work, let's just hypothetically say, let's add on another row, which we will talk about how we're going to do that if you haven't realized it. Let's say 1, 5, 10, 10, 5, 1. Okay? So if we wanted to add one more example, and we wanted to find, for example, x plus y to the 5th power. Well, guess what? We don't need to take this whole thing and multiply it by x plus y. We can just simply use the coefficients. We know the coefficients are going to be 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. And how the rest of this unveils is that we write the first term, which is x. I'll use a different color. Okay, to the highest degree, which is 5. And then the next term is going to be a decrease of 1 degree. And then another decrease of another degree, another degree, another degree, and 0. Then once we've distributed that x through using this theorem, we can now distribute through the y's. So it's going to be opposite. It's going to start with y to the 0, and it's going to increase by 1. So this is y to the 0, y to the first power, y to the second power, y to the third power, y to the fourth power, and then y to the 5th power. So if you were to clean, I'll put plus signs in between all these terms. If we were to clean this whole thing up, we know that 1 is 1, so we don't need to write that. X to the 5th, y to the 0 is 1, so it's going to be equal to x to the 5th plus 5x to the 4th y plus 10x to the 3rd y squared plus 10x squared y to the 3rd plus 5x, don't need to write the 1 because x to the 1 is x, y to the 4th plus 1 times x to the 0, which is 1, times y to the 5th is y to the 5th. And this is a 2-line process of figuring out a 5th degree expansion, but only using 2 lines versus having to do something like we did for x plus y to the 3rd. So I'm going to give you one more example. What if you had a problem that wasn't x and y, okay? And that's what you're going to encounter in your homework later on. So let's just, for example, do something like this. Okay, let's say we had 2a minus 5. Okay, this is a binomial, and let's take it to the 3rd degree. So we have a choice. You can either multiply everything out and distribute and do something like this, okay? Or you can use the binomial theorem. Because this is a 3rd degree, I'm going to put my coefficients in. I'm going to use the 3rd row of the Pascal triangle. And my first term is 2a. So I'm going to distribute 2a to the highest power through. So 2a to the 3rd power, 2a to the 2nd power, 2a to the 1st power, and then 2a to the 0 power, if you want to write that in. Now, the other term that we have is plus -5 or -5. And so I'm going to do just like I did down here. I'm going to take that -5 and distribute it through. It's going to be to the 0 power, and it's going to increase by 1 every single time. I'll put a plus sign here for now. negative 5 to the first power, negative 5 to the second power, and then negative 5 to the third power. Okay? So at this point, now that we've used the binomial theorem, we're going to go ahead and clean all of these terms up. Well, 1 is just times whatever, is just what it is. So it's going to be 2a to the third, so that's going to be 8a to the third times, I'll just put in negative 5. We'll do one step at a time. Plus 3 times 4a squared times negative 5. Okay, because negative 5 to the first power is negative 5. Plus 3 times 6, well, I'll just hold off on that, just write 2a. And then negative 5 times squared is 25. Plus 1 times 2a to the first, which is 1. Anything to the 0 power is 1. So this is just 1. And then we get negative 125. So it could go a little bit further. For this term right here, we have negative 5 times 8 is negative 40a to the third. This term right here, includes this piece right here, is 4 times 3, which is 12, times negative 5, which is negative 60a squared. And then we have this thing condenses down to 3 times 2, which is 6, times 25 is 150, and a. And then we have that minus 125 at the end. So without doing way too much distribution and using the binomial theorem, we're able to expand this crazy binomial into a polynomial in just a couple of lines. All right?